Sometimes, some things seem like a really good idea in principle, up until someone points out that those pesky laws of physics mean that it is actually much, much harder to do than it looks. One of those ideas is the space elevator, something that's been around as an idea since 1895, but it wasn't until the 1960s that it was actually thought to be possible. Since then, there has been a lot of work being done by the likes of NASA, the Japanese Space Agency, and private companies to try and make it a reality. But as of yet, it's a bit like creating a fully functional fusion reactor in that it's just around the corner, but we appear to be driving around a giant roundabout. The basic idea is pretty simple. You place a satellite in a geosynchronous orbit around the Earth at 35,768 kilometers, so that it stays in the same place above the surface. You then lower a 35,768 kilometer long cable down to the Earth and fix it in position, while at the same time a counterweight would be attached to another cable. But this time, the counterweight would be extended away from the satellite in the opposite direction into space. This would allow the center of mass to stay at the position of the geostationary satellite. You can then use climbers, similar to lift cars, to climb up and down the cable to deliver goods and people into space far more cost-effectively on a cost per kilogram basis than launching a rocket. At a speed of 300 kilometers per hour, it would still take about 5 days for the climber to reach the satellite, and more to go higher, to reach an escape velocity orbit on the outward extending tether. But, as they say, the devil is in the details, and in this case, the details mostly revolve around the laws of physics. It was in 1895 when, inspired by the Eiffel Tower, a proposal was made to build a tower from the Earth up to the geostationary orbit at 35,768 kilometers. Any objects that climbed up the tower would attain horizontal velocity, and if a satellite were to be released at the top of the tower, it would stay at that point in orbit and not fall back down to Earth. The problem here is that the weight of the tower would be so great that its base would have to be hundreds of kilometers across so that it wouldn't buckle under its own weight. This was clearly an impractical idea. But some 60-odd years later, in 1960, the concept was independently developed again, and in the mid-1970s, further work was done. Both approaches use the idea of a geosynchronous satellite tethered to the Earth via a very long cable. The later researcher, who was an aerospace engineer for both NASA and the Air Force Research Laboratory, went much further, conducting much more research into every aspect of it. This idea remained obscure until 1979, when a science fiction novel was published in which engineers built a space elevator on top of a mountain on a fictional island at the equator. Now, these ideas seem all well and good on the surface, but the geostationary satellite with a cable hanging down to the Earth suffers from significant challenges. The laws of physics impose constraints that make the concept far more difficult to realize than it initially appears. The materials required for such a structure would need to be incredibly strong, yet lightweight, and the engineering hurdles, from atmospheric interference to orbital mechanics, present enormous obstacles. Despite decades of research and theoretical advancements, the space elevator remains an elusive dream, always just out of reach. The same problem as building the giant tower as proposed before exists with the space elevator cable. The weight of the cable hanging from the top would be so great that it would snap long before it ever made it to the Earth's surface. This is, of course, assuming it was made out of something like steel, which most elevator car cables are constructed from. The issue was recognized and a solution was suggested. The cable would get progressively thicker as it got higher and higher, reaching its maximum width when attached to the satellite. This design ensures that the stress along the cable remains consistent at any point along its length, a concept known as the taper. At the very top of the cable, it would have to support the weight of all the cable below it, whereas at the very bottom, where it's attached to the Earth, it would be very thin because there is no weight pulling down on it at that end. Additionally, the design would need to account for the weight of the climbers and the load being transported, plus a safety margin. This is where the laws of physics really start to interfere with the idea. Steel is a very strong material, but it's also heavy, with a specific strength of 0.63 megapascals. The longest theoretical steel cable that could be hung vertically without snapping under its own weight would be about 10 to 12 kilometers, depending on the type of steel, its construction, and its breaking strength. However, when dealing with lengths of hundreds or thousands of kilometers, steel isn't strong enough to hold its own weight without becoming exponentially thicker at one end. If you look at the taper ratio for some materials, steel, while strong, has a much greater density, resulting in a taper ratio of 1.6 times 10 to the 33rd. This means that to hold a steel cable vertically at 35,768 kilometers long, the thickness at the top would be wider than the known universe. Any material with a specific strength greater than 48 megapascals will have much lower taper ratios. For example, single-wall carbon nanotubes have a tensile strength 26 times that of steel and a specific strength of 100, giving them a taper ratio of only 1.6. Whatever material is used must be not only incredibly strong, but also incredibly light. So far, carbon nanotubes are among the best options available. These are made from football-shaped molecules consisting of 60 carbon atoms, which are then stretched to create a tube-like structure. Meanwhile, the digital world has evolved significantly over the past few decades. Since the early days of the World Wide Web in 1993, it has grown from basic websites into a complete digital ecosystem. Back then, few people considered the possibility of their personal details being harvested from websites, bought and sold by anonymous companies to anyone willing to pay for them. But 30 years later, the digital revolution that many dreamed of has turned into a digital nightmare for some. Our dependence on digital technology has transformed what was once private and confidential into a massive source of revenue for online tech giants, fueled by data brokers, companies that buy and sell data to anyone who wants it. This data can include emails, names, current and past addresses, phone numbers, age, occupation, and much more. For those working in government, the military, civil services, or high-profile positions, this data can pose a security risk or even a personal safety threat. While it's possible to request that these companies delete the data they hold, with over 750 data brokers worldwide, the process is overwhelming. This is where services that specialize in data removal come into play. Since 2010, such services have helped individuals remove their personal information from data brokers in the US, UK, and Europe. The process is simple. Users select a plan, fill out an online application, and the service contacts hundreds of data brokers to request removal. Users receive regular privacy reports showing where their data was found and where it was removed. These services can be used for individuals or families, and discounts are often available for those who sign up through specific links or QR codes. For those who value their privacy, exploring these options is a worthwhile step in regaining control over personal data in an increasingly interconnected world. In computer simulations, a thread just 1 millimeter in diameter had a theoretical breaking length of greater than 10,000 kilometers and could hold a mass of 20 tons. However, the problem here is that the longest carbon nanotube we've been able to make so far is about half a meter long, and nobody knows quite how to make the 100,000 kilometer long thread required to build a space elevator. This is where the focus has been, to try and create materials that have a very high tensile strength to density ratio. The newest developments so far have been graphene ribbons made of perfect two-dimensional sheets of carbon, which are expected to have breaking lengths of 5,000 to 6,000 kilometers and a specific strength of 60 megapascals. However, if this were to be done on Mars, it would be much easier. The gravity on Mars is 38% that of Earth, yet it rotates at a similar speed. This means that the tether required for a space elevator on Mars would be much shorter, as the area stationary orbit is only 17,032 kilometers, thus requiring a lower specific strength. Existing materials such as Kevlar would be strong enough to produce such a tether. The other problem with Mars would be that the Martian moon Phobos is in a low orbit that intersects the equator twice a day, right where the elevator would be placed. But there is a silver lining. Phobos is projected to contain high amounts of carbon, so if carbon nanotubes were to be the tether material, there could be a large supply near Mars without needing to ship it from Earth. All of these ideas assume that we have a method of getting the required material into orbit in much greater quantities than we currently can. It might take hundreds or thousands of launches to build the first space elevator. It would also likely rely on capturing an asteroid to serve as the counterweight, though another option would be to gather space junk from nearby graveyard orbits and lower orbits. However, we still haven't come up with a practical way to do this at scale, so capturing an asteroid might be the more feasible option. Once the first space elevator was built, subsequent ones would be easier, because they could use the first elevator to transport materials into orbit. Additionally, if the counterweight cable extended far enough, reaching a radius of 53,100 kilometers, it could serve as a launching platform. A space probe released from that point would already be at Earth's escape velocity. Other proposals have suggested cables as long as 144,000 kilometers, which would provide enough velocity to send probes as far as Jupiter. In the last 20 years, there has been much discussion about the feasibility of space elevators. Ultimately, the success of this concept hinges on our ability to create a tether that is light enough, strong enough, and long enough to make it possible. Whether this idea ever gets off the ground, pun intended, remains to be seen. The biggest hurdle in constructing a space elevator isn't just material strength, it's surviving the gauntlet of space hazards. Between 100 to 800 kilometers, altitude lies the most dangerous zone, where atomic oxygen erosion, micrometeorite impacts, and radiation would relentlessly attack the tether. New research suggests coating carbon nanotubes with boron nitride could provide crucial protection, potentially doubling the cable's lifespan in this hostile environment. Recent experiments on the International Space Station have shown promising results with these composite nanomaterials, resisting degradation far better than pure carbon structures. Interestingly, the economics might work in favor of space elevators sooner than expected. Current projections suggest that if launch costs remain above $500 per kilogram, a space elevator could become economically viable, even with construction costs exceeding $20 billion. With SpaceX's Starship potentially lowering costs to $100 per kilogram, the business case becomes more challenging. However, the elevator's unique advantage lies in its ability to transport fragile payloads, delicate space telescopes, prefabricated space station modules, and even living organisms could ascend gently over days, rather than enduring violent rocket launches. A fascinating alternative approach being explored is the lunar space elevator. Since the moon's gravity is only 1/6 of Earth's and it lacks an atmosphere, the required tensile strength drops dramatically. Current materials like Xylon or M5 fiber could theoretically support a lunar elevator. The most promising anchor point would be at the moon's equator near the rim of Shackleton Crater, which offers both stable terrain and near-permanent sunlight for power. Such an elevator could transport mined lunar resources to Earth-Moon Lagrange points, serving as stepping stones for deeper space exploration. The most unexpected development comes from biomimicry research. Scientists studying spider silk's remarkable properties have engineered recombinant proteins that, when combined with carbon nanotubes, create a hybrid material with unprecedented toughness. Early tests show these bio-nanocomposites can self-heal minor damage when exposed to certain wavelengths of light, a critical feature for maintaining a space elevator's structural integrity over decades of use. While still in early stages, this fusion of biology and nanotechnology might finally provide the breakthrough needed for practical tether construction. On the orbital mechanics front, new simulations suggest that actively controlling the elevator's oscillation could solve one of the most daunting engineering challenges. By using electromagnetic actuators along the tether and AI-driven predictive algorithms, harmful vibrations induced by weather systems, spacecraft docking, or solar wind pressure could be dampened in real time. This dynamic stabilization approach might eliminate the need for prohibitively massive counterweights, instead relying on precise energy distribution along the cable's length. The geopolitical implications are equally fascinating. Current space law, based on the Outer Space Treaty, doesn't clearly address space elevator operations. Legal scholars warn that whichever nation or corporation builds the first elevator could effectively control access to Earth orbit, sparking potential conflicts. Some propose designating elevator infrastructure as common heritage of mankind, similar to international seabed regulations, but reaching consensus among spacefaring nations remains challenging. As climate change intensifies, an unexpected benefit emerges. Space elevators could dramatically reduce the carbon footprint of space access. Unlike rocket launches that burn hundreds of tons of fuel per mission, elevators would use clean electrical power, potentially making space tourism and industrialization environmentally sustainable. Some designs even incorporate solar power generation along the tether's length, turning the structure into a massive orbital power plant that beams energy back to Earth. The psychological aspect of space elevators presents another intriguing dimension. Unlike the violent experience of rocket launches, a 5-day ascent in a pressurized climber cabin could offer passengers breathtaking views while acclimating gradually to microgravity. Architects are already conceptualizing these climbers as luxury hotels with observation decks, research labs, and even hydroponic gardens to supply fresh food during the journey. This gentle transition might make space accessible to those who could never withstand traditional launches. While the technical challenges remain formidable, the convergence of material science, AI, and sustainable engineering is bringing this centuries-old dream closer to reality than ever before. The coming decade may determine whether humanity takes this revolutionary step toward the stars or if the space elevator remains forever just beyond our grasp. The most radical new design concept flips traditional thinking entirely. Instead of building from Earth up, engineers are now seriously considering building down from space. This top-down approach would use captured asteroids as both counterweight and material source, with nanofactories in orbit processing raw asteroid material into carbon nanotube strands that gradually extend toward Earth's surface. This method bypasses the need for massive initial launches from Earth and could potentially construct the elevator in just 5 to 7 years, once the orbital infrastructure is established. Recent advances in autonomous space manufacturing make this approach increasingly plausible. Surprisingly, the key to making space elevators economically viable may lie in an unexpected application: space debris cleanup. The elevator's tether could double as a cosmic fishing net, using electromagnetic fields to capture and deorbit dangerous space junk. Each piece of debris collected could be processed for valuable materials or used as additional counterweight mass. This dual-purpose functionality could generate revenue streams to offset construction costs while solving the growing orbital debris crisis, a brilliant example of killing two birds with one stone. The medical field is contributing unexpected breakthroughs through cancer research. Scientists studying the extraordinary strength of cellular microtubules have discovered protein structures that, when combined with synthetic polymers, create a material with 80% of carbon nanotube strength, but far greater flexibility. These biohybrid cables could withstand the dynamic stresses of an elevator tether while being easier to manufacture at scale. Early prototypes already show promise in laboratory conditions, though space environment testing remains to be done. Climate science has revealed an unexpected advantage regarding elevator placement. Detailed atmospheric modeling shows that climate change is causing the equatorial zone to expand, meaning future elevator bases might need to be located slightly further from the equator than originally planned. Conversely, the warming oceans are creating more stable, high-pressure zones that could provide ideal anchor point locations with consistently calm weather. A rare case of global warming potentially helping space infrastructure projects. The most surprising potential application comes from quantum physics research. Experiments with quantum entangled materials suggest it might one day be possible to create a virtual counterweight using entangled particles, dramatically reducing the actual mass needed at the orbital end. While still theoretical, this approach could eliminate the need for asteroid capture entirely. Researchers at CERN and Fermilab have begun preliminary experiments to test whether quantum effects could be harnessed in this revolutionary way. Military strategists are quietly studying space elevators as potential game changers in global security. Unlike vulnerable rocket launch sites, an elevator would be nearly impossible to disable completely, even if severed. The orbital portion could remain functional as a space station. Some designs incorporate multiple redundant tethers that could automatically reconfigure if damaged. This inherent resilience makes space elevators particularly attractive for ensuring continuous access to orbit regardless of terrestrial conflicts. The psychological impact on human space exploration could be profound. With routine elevator access, astronauts might bring families to orbit, leading to the first generation of children raised partially in microgravity. Developmental biologists are already studying how prolonged weightlessness affects mammalian reproduction, with recent ISS experiments showing mouse embryos developing normally in space up to a certain stage. This research could pave the way for permanent, off-world communities connected to Earth by the elevator. Perhaps most intriguing is how space elevators could transform astronomy. A tether stretching through the atmosphere would enable unprecedented atmospheric studies at every altitude simultaneously. Scientists envision mounting sensors along the entire length to create the most detailed vertical profile of Earth's atmosphere ever obtained. Data crucial for climate modeling and weather prediction. The elevator could also serve as a gigantic radio antenna or support telescopes at altitudes impossible to maintain otherwise. A final note of appreciation is extended to all supporters for their ongoing contributions.